Presenting on the model competition and law discovery in differential equations.
Thanks, Ira. Thanks for the introduction. Good evening, everyone. My name is Tosh Shahrtash. I would love to thank the Semioid organizers for putting together this fantastic opportunity and this amazing conference, and to really make this happen. And not just this, but also all the resources. I was just talking about how this past summer it was my first real experience with Simio than to really, dive deep and learn about all these resources that are available in the textbook. So that was really for me, it was a, really career changing kind of experience because uh, I've been traditionally I'm a pure math person. So for years, my differential equation classes emphasized theory and solutions to differential equations, as we all do, systems of differential equations, numerical methods, this, but we never talked about how differential equations really come to be. After being exposed to the modeling first approach, thanks to Simio, I started rethinking what it really means to introduce our undergraduate students to differential equations. Uh, at the same time, uh, AI tools have become much better compared to what they were before, and they have become good enough to generate realistic data and virtual experiments. So this talk really sits right at the intersection of these two. My my exposure to the modeling first approach and AI models becoming good enough to generate um, data. So in in this talk, I will outline a structure that uses AI as infrastructure and uses Python as a diagnostic tool. And I will talk about some of the assignments, two of my two structured assignments that I have developed and I have incorporated in my newer version of differential equations. So as I said here, basically this is all about shifting my own attention from solving differential equations to how a differential equation comes to be. I have to emphasize that the role of AI here is not solving. AI is our infrastructure. And the two assignments that I will talk about are model competition and maker finder exchange. So, in many of my earlier differential equation courses, we always, of course, talked about applied examples. Applied examples were always there, and students were always told that this differential equation uh, models the system, but students rarely saw the data that led to the model. Uh, so in practice, equations really did not really emerge from evidence. And but then I always think to myself that in practice, in science, in engineering, technology industry, where our engineering students are going to work, equations don't just show up, and they show up as data, and everything that follows that depends on how they handle the data and how they interpret the data. Uh, so why don't our differential equation courses always start with data? Well, as we all know, there are real barriers here. We don't have labs in our classes. At least I don't have labs in my differential equation courses. We don't have sensors. We don't have we don't all, a lot of the systems are not easily measurable in our classroom settings. So, and that was really the main reason why a lot of us, although we really want that, we can't really start with data. And this is exactly where AI could become very useful and where AI shines not as a solver, but again as the infrastructure. This allows us to AI would actually allow us to generate physics consistent and synthetic data from virtual experiments that would be otherwise impractical. So here. we will use data, we will use AI and basically in my setup uh, because AI enables science consistent and synthetic data and controlled variation of conditions and parameters. AI does not decide the governing law. AI does not interpret evidence or replace mathematical judgment in our setup. So this is one of my assignments here. This is model competition is my first structured assignment that I use in my differential equation courses more recently. And basically, the core idea is differential equations are treated as competing hypotheses, and data is used to eliminate models here. So what we do is I provide students are given a large data set representing measurements of a single state variable. And together with that data set, it's a large data set, three candidate differential equations. So this is what students are given for that assignment. One large set of data and three candidate differential equations. Their task is to determine which differential equation governs the data, justify the selection, and validate it. And in their deliverable, they need to explain what structural evidence supports the selected model and why the alternative models were rejected in their decision. So this is our basically the model competition. So in order to do this, of course, I have to generate my data set, and the quality of that data set uh, really depends entirely on how we design our prompt. Uh, we must specify all the variables and parameters that we're basically requiring. Otherwise, the quality of the data would not be very uh, reflecting of the realistic, physical systems. So these are the practices for generating usable data and data that is realistic and is consistent with our physics laws, basically. So we need to specify what is being measured here, state variables, units. We need to specify how the system is observed here, time windows, sampling rate, our initial condition. We need to specify the expected qualitative behavior. We need to describe if it's increasing, decreasing equilibriums. Uh, and we also need to specify our constraints that the data must basically respect and also use simple and transparent formats. I usually use just a CSV file for my students, although I'm looking forward to sort of expanding this to some other large formats like Parquet and things like that. Um, so here's one of my prompt examples. So in this example, I was trying to generate a large data set for my students for this particular experiment. So this was the prompt to generate a CSV data set that simulates measuring CPU temperatures under sustained load 1,000 times sampled at uniform time steps. And then the second instruction specifies use a single lump temperature state, T of T, in Celsius. The temperature should rise monotonically in its initial value and approach stable equilibrium determined by an ambient temperature T of A. Generate the dataset by numerically integrating a single first order autonomous differential equation that exactly governs the system. So we're trying to make sure that our data is actually 100% consistent with the differential equation that governs it. Ensure the equation and dataset are internally consistent and reflect the specific qualitative behavior. Output is CSV with two columns here. And after the dataset, again, state the governing differential equation, parameter values, and initial condition used. So this is an example of one of the prompts that I recently used in my fall semester course to generate large data for my students, the kind of data that they can't easily just, just by, eyeballing the information, sort of come up with it. And then this would give him one piece, and then this comes with three differential equations. Now, basically, if you think about this without and what I do is here I generate because I my classes usually have 15 students. I generate 15 different sets of data. And I do that just by changing the initial condition. I don't really need to change the differential equation or the model. Only by changing the differential equation, which could be included in the original prompt, we can create 15 different CSV files that you can provide to your students. So they're not really working with the same data, they have different data, but they all are initiated from the same governing rule here. And really, without AI, this is one of those areas giving each student a different data set that comes from the same law would not be very practical. And and one of the things that I notice is students compare their reasonings without really comparing their answers because they're dealing with different data sets, but the reasonings are actually similar here because it's the data sets, the 15 data sets that were generated, they all were coming from the same differential equation. Uh, and basically, what students begin to notice is while trajectories are different, certain features remain invariant. And that's exactly what they want them to see in a differential equation and to understand in a differential equation that the rate-state relationship, for example, remains the same, even though our data sets are not exactly the same, or the equilibrium, or eventually the governing law. Now, as for the student discovery, how do students basically reject two of the models and justify the remaining third model? It has two phases. Of course, all of this is done with Python. We use Jupyter notebooks in our classes, and all of these are embedded. So what they do is, of course, reading behavior from data. So this is phase one. They're trying to go from data to governing structure. They plot TFT, they read the behavior, and then the instantaneous rate, DT/dt. They try to test autonomy. They plot DT/dt versus T, and they look for where exactly what is the relationship here? Is it linear? Is it quadratic? What is the concavity like here? So based on that, this will be basically phase one of what they do. And so after those structural inferences, this is the part that students formulate candidate models. So the three ones that they're usually given, the constant, linear, and quadratic. And basically they try to check the trajectory of each of these and see if they approach the correct equilibrium, if the trajectory actually matches their data set, or one of the things that we also consider is RMSE for each of these basically models. So this is one of the assignments that I use in my basically, as I said, um, one data set together with three differential equations. Another assignment that I have incorporated in my classes is the maker finder model discovery. This is kind of similar to the other one, but for this one, students are put in groups of two, and one of the students will be tapped as the maker, and the other one will be the finder in this group. So the governing laws or the differential equations in this assignment, they all come from the textbook, which could be ZIL. So they use, for example, the third chapter of ZIL for their modeling and for their first order differential equations. And the maker's role here is basically the maker will pick one of the differential equations from the chapter and is an experimental designer. So they select a differential equation and they generate a data set and they would hide the law from the finder. And then they will hand it over to the finder. So the finder will have the data set and all they receive is the data set. And they must use the diagnostics to infer the law and justify it mathematically. So this way, each group of two between the maker and the finder, they have their own experiment, and they get to see how the other person gets to uncover uh, the experiment that was designed basically by the maker. Um, so in this type of assignment, these are the kind of deliverables that I would expect students to hand in. Uh, for the maker, they need to have a data set. They need to create high resolution time series with 1,000 samples. Everything needs to be clearly labeled. Governing differential equations, this has to be sealed because they should not be revealed to the finder. And it has to be an explicit form. The parameters should be clarified, and the model context, the description of the model phenomenon. And the finder's deliverables are the diagnostic figures, everything that has been done with Python, and the justifications, including the structural reasonings and why the alternative forms were rejected in this model. And of course, the evidence of consistency. So these are basically the two assignments that I incorporate using AI generated data sets in my classes. And I think this is pretty much it. So that was everything that I wanted to share.